Welcome back. In this video, we are going to solve example 5.10 that is taken from chapter number 5, Torsion, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is the 6061 T6 aluminum shaft shown in figure 5.27 has a cross-sectional area in the shape of equilateral triangle. Determine the largest torque T that can be applied to the end of the shaft if allowable shear stress is 8 ksi and angle of twist at its end is restricted to allowable angle of twist is 0.02 radian. How much torque can be applied to a shaft of circular cross section made from the same amount of material? So here we have two things: determine the largest torque and how much torque is applied when same amount of material is used for circular cross section. So let's start with the solution. What we will do first is that if you cut this aluminum shaft at any length, clear? So you have to find the torque. So when you cut it at any length, for example, if we are cutting it through this much length, and we will draw the free body diagram, so it will be like this. I will draw it roughly. For example, this is the shaft, clear, and this will be the section like this, clear. And at this end you can see you have this torque T. So what will be, this is in this will be in clockwise direction. So for balancing it, our resultant or internal torque will be in counterclockwise direction T. So what we will get is that we have this T is equal to counterclockwise direction. Okay, and this torque is the resultant internal torque. Now using formula for tau max and maximum angle of twist using by table 5.1, that is pasted over here. You can see this is table 5.1 that is available in the book. I can also show you, this is available at page number 226. So you can see here we have three shapes: square shape, equilateral triangle, and ellipse. So our shape is equilateral. So you can see this is the maximum shear stress. I will write the formula: tau max is equal to 20 multiplied by T divided by A cube. Now here you can see equilateral triangle A. So here you can see this value is A. So A is equal to 1.5 inch. And you can see the second is allowable angle of twist at the end, which is 46 TL divided by A power 4 into G, where G is modulus of rigidity. So we have all the values. What we will do is that we will find this torque T, because we have been asked to find the allowable torque T. So using this first formula, and this is the second formula. So using 1, we have this maximum or allowable shear stress is 20 times T divided by A cube. So from here what we will get, this T will be equal to allowable shear stress multiplied by A cube divided by allowable shear stress divided by 20. So what we will do is that, again you can see allowable shear stress is 8 ksi, and we will put the value. So 8 into 10 raised to power 3 pound per square inch. A is also given as 1.5. So 1.5 divided by 20 is equal to T. So from here we will get this T, and we will calculate it. 8 into 1000 multiply by this 1.5 cube. So multiply by 1.5 power 3 is equal to 27,000 divided by 20. So answer divided by 20 will give you this torque T, and that is equal to 1350 pounds into inch. Now this is the allowable torque based on, I will write is allowable torque based on allowable shearing stress. Clear? Now what we will do is that we will find this torque T by using maximum or allowable angle of twist. Okay, so we have formula number 2, which is allowable angle of twist is 46 times T into L divided by A power 4 into G. So from here we will get this T will be equal to allowable angle of twist multiplied by A power 4 into G divided by 46 times L. Now allowable angle of twist is given as 0.02 radian. Clear? And we will write this T is equal to 0.02 times A is 1.5 power 4. What is G? So we will go to the end of the table and we will find this G value. This is given as 6061 T6 aluminum. So you have to go at the end of the book and you have to check the average mechanical property table, and the unit should be in US customary. Now you can see that here we have this aluminum T661T, and what will be the value of G? So G you can see 3.7 into 10 raised to power 3 KSI. Copy this value, 3.7 into 10 raised to power 3 KSI divided by 46 times length is given as 4 feet. So we will convert 4 and 1 feet is 12 inch. So 4 into 12 inch. Clear? And this T will be equal to 0.02 multiplied by 1.5 power 4 multiplied by 3.7 into 10 raised to power 3. And we will remove this kilo as well. So this is also 10 raised to power 3 pound per square inch divided by 46 into 4 into 12 inch. So let's calculate the value. So 0.02 multiplied by 1.5 power 4 multiplied by 3.7 multiplied by 10 raised to power 6, because 10 raised to power 3 multiplied by 10 raised to power 3 is 10 raised to power 6. Okay, so we will get this torque is equal to 374,625 divided by the value, which is 46 multiplied by 4 multiplied by 12 is 2208. Now 374,625 divided by 2208 will give you 169.667 pounds into inch. So we can round it off as torque is equal to 170 pounds into inch. Okay. So we can see we have two torque. One is 1350 pounds into inch and the second one is 170 pound into inch. So what we will do is that I will write it by comparison. The torque is limited due to angle of twist. Our answer is allowable maximum torque is 170 pounds into inch. Why we have chosen this as answer? Because when you put this value in this formula, it will exceed than the allowable stress given as 8 KSI. But when you put it in this, it will give you the allowable shear stress that will be our maximum shear stress that will be less than the allowable shear stress. But what if you put this value in this angle of twist? So your maximum angle of twist will be greater than the allowable. That's why we choose this torque. Now we'll move toward the second part, that how much torque can be applied on the shaft of cross section made from the same material. Okay, circular cross section. So what we will do is that if you can see that volume of circular rod is equal to volume of equilateral triangle. Clear? So we know that this will be equal to area of circular rod multiplied by length, and this area of equilateral triangle multiplied by its length, because we have to say use the same volume. So both lengths will be same, so it will be cancelled. So area of circular rod will be equal to area of equilateral triangle. And we know that area of circular rod is equal to pi c square, where c is the radius. And what about equilateral triangle? So area of equilateral triangle is equal to 1 over 2 base into height. Okay, so what we will do is that you can see here that this is base, which is 1.5, and this angle is 60 degrees. So I will draw it over here so that you have a clear understanding. So this base is 1.5 inch and this angle is 60. So we will need this height h. And you can see that if you take sine of 60 degree, so this sine of 60 degree is equal to this perpendicular h divided by this hypotenuse, which is again 1.5, because it is equilateral triangle. So this height will be equal to 1.5 times sine of 60 degree. So put the value 1 over 2, b is 1.5 and h is 1.5 times sine of 60 degree is equal to pi c square. So we are in need of c, so c square is equal to 1 by 2 into 1.5 square into sine of 60 degree divided by this pi. So let's calculate it. 1.5 square multiplied by sine of 60, again 1.5 square multiplied by sine of 60 divided by 2 multiplied by pi. Okay, so we will get this c square is 0.310. So c will be equal to under root 0.310. So I will take the square root of this answer. So you can see this is equal to 0.5568 inch. And c will be equal to 0.557 inch. Now we have this c. So we are going to find out the maximum shear stress, torque. So we know that maximum shear stress is equal to T into C divided by J. So from here we will get same material is used, so allowable or maximum shear stress will be same. So tau max or allowable shear stress into J divided by C. So maximum or allowable shear stress is given as 8 KSI. So I will put the value. So 8 into 10 raised to the power 3 multiplied by J. So J is pi by 2C power 4. So C is 0.557. Clear? Power 4. Divide by this C 0.557 will give you the allowable torque. Okay. So let's calculate it. So 8.8 into 10 raised to the power 3 multiply by this pi multiply by 0.557 power 4 divide by 2 multiply by 0.557, and you can see this is 2171.5 pounds into inch. Okay, so I can write it. Torque is equal, allowable torque on a circular shaft of same material is this much. Okay, now we will calculate the torque based on the maximum or allowable angle of twist, that is equal to T into L divided by jg. So from here we will have this torque is equal to allowable angle of twist into J multiplied by G divided by this L. So we'll put the value allowable angle of twist is 0.02 radian. So 0.02 J is pi by 2, C power 4 and C is 0.557 power 4 multiplied by G. And G, you can see we have taken this value 3.7 into 10 raised to the power 3 KSI. So I can write it 3.7 into 10 raised to the power 6 PSI divided by length, and length is 4 feet. So 4 multiplied by 12 will give you the length in inch. Okay, we will solve this 0.02 multiplied by this pi multiplied by 0.557 power 4 multiply by 3.7 into 10 raised to the power 6 and divide by this 2 multiplied by 4 multiplied by 12, and you can see you have torque is equal to 233 pounds into inch. Okay, now we have two torque for circular shaft, that this one is based on allowable shear stress and this one is based on maximum angle or allowable angle of twist. So by comparison our answer will be torque is equal to 223 pounds into inch due to limitation in angle of twist, and that will be the answer. Again, what if you put this value in this maximum shear stress? So your maximum shear stress will be less than the allowable shear stress. But what if you put this torque in this angle of twist? So it will exceed than the allowable. That's why our answer is 233 pounds into inch. Now you can see that if you use triangular bar, so your allowable torque was 170 pound. So for equilateral shaft, maximum allowable torque is 170 pounds into inch, and for same amount of circular shaft or same material and same amount of circular shaft, torque is 233 pounds into inch. So we can compare which one is taking more torque. So again you can see that circular shaft is taking more torque, and if you find the how much percentage it can take, so 233 minus 170 divided by 170 multiply by 100 is 137. So circular shaft is taking more torque, 37% more torque than the equilateral triangle shaft. So hence we can conclude that if you use the same amount of circular shaft, so it will be better for this load problem or torque, and that will take too much torque than this equilateral triangle. So this was all about example 5.10. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.